Hi, welcome to Teardown Tuesday. The humble hard drive. You've seen them, you probably take them for granted. This is a modern 2 terabyte, 3.5 inch hard drive that you'd get in a typical desktop computer. And they're available in pretty small sizes these days, especially for their size. Incredible. These can go up to 4 terabyte in the 3.5 inch size. This is the smallest current form factor you can buy, the 1.8 inch, and they're available in up to 300 odd gigabytes in these sizes. But that wasn't always the case. These things have had an amazing evolution back from the mid-50s when they were developed by IBM. And wow, I can remember buying my first hard drive mid-80s or thereabouts, 20 megabytes. That's not 20 gigabytes, it's 20 megabytes, let alone terabytes that you can get in these things. Incredible. Cost me about $300 or thereabouts. Nowadays you can get like what, a terabyte for under $100? You're kidding me. So these are fascinating technology. There's developed in density by many orders of magnitude over many decades, not to mention reducing in cost as well. So I thought we'd crack one open, have a look at the technology inside, but not one of these weird ass modern ones. No, I thought we'd go a bit retro, late 70s, early 80s. Great period. Let me get it for you. Hang on, this could take a bit. Let me move the chair out of the way. This is a real hard drive, folks. The mother of all hard drives. Let's check it out. Here we go. Hang on. Bend the legs. Ta-da! This is a hard drive. Woohoo! It's an IBM hard drive. Late 70s, early 80s, not sure of the exact year. Whopping 10 megabytes. And yes, it weighs 38.5 kilos, or about 85 pounds. It's an absolute monster. We're going to tear this sucker down, and don't worry about me dropping it. No worries. Wearing Australian safety boots. Beauty. Let's go. And if you're wondering what this thing was worth back in late 70s, early 80s, about $250,000. Beauty. And yes, folks, I wasn't kidding. This sucker is really worth $250,000, or it was worth $250,000 back in late 70s, early 80s. And this particular unit was used well into the 80s because they didn't want to write off the cost of these things. They were cost so much money to install, service and maintain, even though hard drives were dropping, even big server ones like this, dropping by orders of magnitude. They didn't want to write off that cost very quickly. So it was still used for quite some time. And this particular one is actually from a bank. It's from the ANZ Bank here in Australia, and it was used to presumably store all of the banking records. And no, it has been securely wiped, so no one's credit card numbers are on here. Not that did we have credit cards back in the 80s? Maybe bank card. Anyway, this is an IBM. Let's have a look. It's got the original sticker on it here. IBM, there it is, IBM Asterisk 397X. So I assume it's like a 397X series or something, or 397X series, something like that. I'm not sure. Haven't been able to find much info on it. So if people have any information on that, please let me know. And check out this funky little temperature dial here. They've actually got, it is about halfway, it is around about 23, 24 degrees here in the lab. And this is completely passive. Now this thing is an absolute beast. It's actually designed on a sliding chassis, hence the handle here. It's got the big carry handle and handle on the other side. So this chunk of metal on the back here is actually a sliding frame designed to slide into a rack there. And we can already see some of the stuff. Perhaps we've got some cabling with some beauty connectors on here. Absolute classics. Look at that. And yeah, so this thing was designed to slide in with the aid of a tool. You can't have, even back then they still had OH&S, and you couldn't have people lifting up near 40 kilo or 90-pound units and, you know, shoving them into racks. So they had some sort of tool to help lift them up and put them into the rack. And you can see that they had shock and vibration mounts as well. You can actually see the compliance in that one. If I give it a bit of a wobble, you can see the compliance in the rubber there. That would dampen shock and vibration from the both from the rack and into the hard drive, and also outwards. And you know, that would be very cleverly designed so that it avoids any resonant modes during operation and all sorts of stuff. And these would be ultra reliable hard drives. So you know, these are in banks storing data. This is serious, and this is why these suckers cost, back in those days, $250,000 each. Do you believe it? And you may have noticed on the unit this little port here. They've actually got one here and one on the other side of the unit. What was this for? It's actually for pressurized halon gas, which is actually quite a dangerous gas to be pumped into these hard drives, so they operate under that halon gas, and it's actually a fire suppressant. Now, this halon gas wasn't just used in the hard drive itself to save the data, and there's the other port over on that side there. So they would pump pressurized halon gas into this thing, but the entire rooms that these things were housed in, the computer server rooms, had halon gas as well, not during operation, but if there was any fire, then they would a big alarm bell would ring off, and you've got like a minute to get out of there or put on your gas mask. Otherwise, you would die, because they would fill the room with this halon gas fire suppressant. They were really serious about protecting the data in these hard drives. And on the back of the unit here, where it slid in, it'd slide in forward like this. Presumably there would be the mate-in multi-pin bus connector under there like that. It'd mate with power and something else here, I'm not sure what, and that would be how it slots into the rack. So this would be the end that goes into the rack, and the handle would be on the other end. And on the front of the unit here, they've got like another port. Maybe that's a some sort of test port, I don't know, as in like a test, like a gas port, or it might be a pressure valve or something like that. I'm not exactly sure what. And we've got some power coming around to this side as well, maybe going into the spindle motor or something, because we've got some heavy duty cabling going on in here. So anyway, we'll find that out when we crack this sucker open. And here we go. Let's take it open. Now, I think we've got one big sort of, you know, die cast slash machined top on the thing. So I think if we undo these hex screws around here, we should just be able to lift up this top part, at least for starters, and see the good stuff, the pornographic stuff, which is the platens. So let's crack this thing open, see what we get. Oh, here we go, folks. This is going to be exciting. I think it seems to be lifting off. Here we go. Let me see. I don't want it to come crashing down. Ta-da! Oh, look at the porn in there. And check this out. What a Bobby Dazzler. Fair dinkum. Oh, it's an absolute cracker, this one. Look at the, we've got 2, 4, 6, 8, 9 platters in here. Single-sided head. So they'd be doing, you know, just over 1 meg per plate. Unbelievable. And if we get in there with the measuring tape, we're looking at 11-inch or thereabouts. You're working the old money with these hard drives. 11-inch platters in there. Beautiful. So this is what $250,000 would buy you in super reliable server storage technology in the late 70s, early 80s. And if you compare and contrast that with, you may have noticed it sitting here, a modern, these came out in mid-90s, so really only, you know, 10, 15 years difference kind of thing between this thing, which is 10 megabytes, to a couple of 100 gig. This was later on, but you know, we're talking 4 orders of magnitude. Look at it. Unbelievable. But if you break these things down, you'll find that they're still essentially working identically. Yeah, the encoding format and the densities and the data rates have all changed. I mean, the data rates inside modern hard drives are absolutely incredible. The serial data rates in and out of the heads, and all the physics with the magnetics has all changed, but they're essentially, the operation is still the same. We've got the platters coated with the magnetic material, we've got the spindle, we've got the actuators, we've got the heads, we've got the head, there's probably a head preamplifier on there, and you know, and the decoding electronics. They're all going to essentially be identical to modern hard drives. And look at the solid machined chassis on these things, absolutely incredible. And if you check out inside the head unit itself, fully O-ring sealed of course, but you'll notice they've also got air filters in there either side. So that air filter down in there would be filtering the halon, pressurized halon gas, which goes into this thing. Now on the bottom here, it looks like we're going to have our spindle motor down in here. That'd be this cover plate down in there. If we take that off, we might be able to look at the spindle motor under there. It looks like a huge monster, and this is almost certainly our actuator motor down here. Now I'm not actually sure how much electronics we're going to find in this thing. I mean, we'll have our amplifier head on the top here on the actuator arm itself. Looks like these are just sort of, looks like some sort of interconnect system. I'll try and get those out later, and flat flex ribbon cable coming over, and it certainly doesn't have the processing in it like modern hard drives do today, that's for sure. Here you go, that wasn't hard at all. Watch this. Just snap that open, look at that. All that customized connector solution that, you know, it's like you won't find you know, solution like that off the shelf. It's just totally customized for this particular unit. No wonder they were charging $250,000 a pop. They had to amortize all the R&D cost of this thing. And it looks like all the data for our heads pops out along all these traces. There's a lot of traces down in there, and it pops down into, it looks like probably, I don't know if there's any electronics under that, but probably down to that main header connector we saw down there. And these flat flexes here, they just pop off here and then going into these two traces down the bottom there, which probably go down to the main interconnect connector down on the back there, presumably. And check it out, folks. I found a genuine hardware bug in this thing. Right inside the channel there. Maybe during servicing. And down on the bottom of the unit here, you can see this custom plastic, a flat flex connector sort of embedded in some plastic like this. That big, huge, couple of 100 pin bus connector joins onto. So that actually does, it looks like, goes straight down to there and then straight onto this paneling down in here. There you go, it goes straight down into there, straight into these connectors, and then straight over into the heads there. So yeah, this thing, you know, it doesn't look like it contains any processing electronics at all, apart from the ASIC. Presumably that would be on the head driver in there, the head amplifier / buffer. That'd be about it. Well, check this out, folks. Look at that date code, February 18th, 1991. So I don't know if it was manufactured in 91 or whether or not they retrofitted a new cable to this thing in 91, but there you go. That's fascinating that they were still manufacturing, if it is 91, they were still manufacturing these 10 megabyte hard drives right up until that time. And it turns out this temperature strip on the back here, which does actually work, by the way, I've had it go up and down in temperature, is just a peel off tape like that they stick on it. There's no mechanism at all inside that. Look at that, it's gone up to 28 now, so it claims. 30, there we go, slowly going up. 32. As I touch this thing, it goes up in temperature. Neat. And if we take the cover plate off the spindle motor here, it looks like, correct me if I'm wrong, but we have a 9-pole, 3-phase induction motor, because there seems to be 3 phases there. There we go, we've got 3 main windings. We've got black, red and white there with the big thick cables like that. There's a green earth wire presumably, and a couple of other signal wires as well. So there you go, that's a bit of a beast. I'm not sure how much mass it actually has to rotate and at what speed, what operational speed this thing would have worked at, but that's a pretty funky looking unit. I like it. And once again we seem to have that date code 9th week 91. So I think this sucker was actually manufactured in 1991. But hey, IBM would have had this, big, decades-long service contracts for these things, and they didn't want to rock the boat. They just wanted to replace them with exactly what they got. So it looks like they were still manufacturing these in 1991. Go figure. But I guess if they did the contract and first designed and manufactured these back in the early 80s or late 70s, it's not much more than a decade service life, which for this kind of industry is not that uncommon at all. And on this interface board here, you can clearly see what's likely a positional sensor, probably some sort of hall sensor or something like that. So they've got one there, and one there. And I just love looking inside these platens. Look at that. Ah, it's a thing of beauty. Joy forever. You can see in here part of the rubber seal as well, which actually goes all the way down the side there, right down here and over and around that into a machined groove in the chassis like that. So that seals this, the air of this section, because the filter is just in between here. So the filter, the air comes in here and then has to go through the filter to get to the rest of it. Now check out the really cool linear slides on here. Look, we've got them machined into these blocks here, and you can see the rollers inside there. So obviously this head, which likely contains like 4 or 5 heads on it, is designed to slide out of this somehow, but haven't quite figured it out yet. I've taken some screws off here, but it's really quite a complex block overall, this whole head system. It really is quite amazing. So I'm still trying to figure out how to slide this damn thing out. And if we take off this black cover here, there's actually a grub screw in the back of this, which then goes onto this spring and pushes that in, and you can see the linear slide in there moving back and forth. Now I can't pull that out, but what that does is that adjusts the head here, so you'll be able, as I move that, you'll be able to see the head just move it, tweaking it back and forth like that. All right, I figured out how to get this whole module out, and with hindsight it was obvious. You had to take out the actuator motor from the bottom first, because that shaft was holding the whole thing in through that little hole down in there like that. So there it is there. So once you get that out from the bottom, you can lift out carefully. You don't scratch the discs. I'm sure there's a better way to do it, but ta-da, we have the entire head assembly. Now these things of course would be designed to be very serviceable. I mean, you aren't going to just throw out, if it fails, you're not going to throw out one of these huge machined die-cast chassis or anything like that. Massively expensive. I mean, this thing costs $250,000. You're going to service the thing. So everything is designed with servicing in mind. If you need to replace the platters, you're going to replace the platters. If you need to replace the heads, you're going to replace those. Any of the, well, there's not much else in it that can fail really, because this is essentially just a spindle motor with a platen, an actuator and some heads, and that's pretty much it. It's just raw data out. But yeah, these things, these are not today's consumer throwaway items. And you can see why they've gone for this flex PCB sort of embedded in this plastic membrane here. It's to get a good sealing around here. You can see it all gunked up right around the bottom around there, and that's, you know, complete airtight seal. So that's how they penetrate this thing, and also right around inside there as well. So that's how they penetrate the main chassis down here while keeping an airtight seal with, you know, how many, you know, 32 heads or whatever having to go through and penetrate and get all the data out of this thing. So that's how they decided to do it, and it's never really seen anything like that before. It's a quite remarkable construction technique. And here's where all the precision engineering comes in with the head. Even though the tolerances on this hard drive are huge compared to today's standards, you can see the heads are able to move very smoothly. Trust me, that is pornographically smooth on those linear bearings in there. Absolutely beautiful. And we've got a total of 32 heads. I thought this was single-sided. I was told it was a single-sided platen, but it's not, because if you get in here, you can see there is 32 heads total. There's actually a head back here, and there's a head up here. I'll show you these in more detail in a second, but you can see that little flex arm there and the one on the top. The heads are a bit out of whack because they're designed to free float, and I'll show you that closer in a sec. But there you go, that one does the upper side of that top plate, this one does the underside of the top plate, so the top surface of the top plate is not used. But we've got 16 heads down there, and we've got another 16 heads back here. So with hard drives, a lot of the access time is going to be taken up with the physical movement of the actuator arm back and forth like that, or swept across the disk. In modern hard drives, you've seen them, you know, sweep back and forth really, really quick. Well, this would do the same thing. It'd move in and out really very quickly, but it takes time to get to the position, settle down before it can read or write the data. So the less distance you have to move like that, the greater your data rate is going to be. And if you've got dual heads, well, you can write twice as much information while moving half the distance. We have a look at these heads in a bit more detail. You can see the armature there. There's really slight pressure. You can see the spring bar in there, designed to just put the required amount of pressure onto the head. And in this example here, you can see that the platter would sit in between the two like that, and then they would rest on the surface, and you'll notice that they're really very compliant and designed to sit very flat on that surface with very minimal amount of pressure. You can probably see one of the little wires on the back side there for the head. And when I said single wire, well, it's actually a dual pair. Look at that. You can see the red and the green in there, hopefully. You can see the arm moving up and down, and that's actually a twisted pair going over and soldered onto the flat flex membrane over there, and very nicely clamped in there. It's got some tubing over it so you don't actually short or pinch out the wires there. Really beautiful construction, and these would all be you know, hand assembled, and somebody's tweaked it with their tongue at the right angle. Ah, beautiful. You might be able to see it a bit clearer there. They've put some tape over the top of that just to anchor the wires in place, just to take the stress out of those before they're soldered, because you don't want any flexion on that or any vibration ruining that solder joint there and getting fatigue on that. So they're de-stressing that with some tape there. Really is beautiful, fine construction technique. I really like it. Imagine what today's modern hard drives are like. Oh, don't even ask. And if you have a close-up of the head there, you can see that, if I can get the pointer in here, you can see that where the two wires were soldered onto, I've actually broken that one off, and that goes into a coil down in there, and it looks like there's a second identical coil on this side, but it's not actually connected there. So if we flip it up like that, you can see, oh, look at that, we've got an individual serial number on there individually serial numbered. Isn't that sexy? Oh, I love it. And the backside, of course, is nothing special, but that would be a rather obscure material ferrite head. Now you'll notice that the head here is not completely flat. It contains these skids either side of it here, and there's two reasons for this. It raises the ferrite head above the surface of the disc by a fixed amount, but the first reason is that it reduces the friction, of course, because the less surface area, the less friction you're going to have. But the second reason they do it is that it forms a little aerodynamic pocket inside there, which helps stabilize and level the head when it's flying over the surface, and that can be very important for repeatability. And that's why the head floats on those little armatures you've seen in there, because it's essentially a self-leveling device. It's not just in a fixed position. It just, floats just above the surface there under aerodynamic pressure. Really neat design. Now, a lot of the early magnetic alloy materials used in these heads are things you've probably never heard of, like molybdenum perm alloy, things like sendust and alphanol. Go figure. But then they moved on to some more amorphous ferromagnetic alloys, and pretty much ferrites dominate the industry these days for heads, even around this era. So this is probably some form of ferrite material. And these new ferrite materials are usually either like a nickel zinc or a magnesium zinc type combination alloy, but they're certainly not just your regular ferrites you'll find in your inductors and stuff like that. These are pretty, obscure materials, alloy materials used for very specific properties, and all has to do with the width and the density and the hardness and all sorts of things that you're trying to get in modern hard drive. The modern ones these days, who knows what they're doing. It's rocket science. Now these heads have to have near zero magnetostriction, it's called, which basically means that this thing can change shape based on the applied magnetic field very slightly. But because this is a highly precision engineered head, even back then, the modern ones today, order of magnitude more sensitive, of course, but even back then you have to be very careful that this thing, when you're writing the ones and zeros to it, changing the magnetic field, that it does not physically change shape, and that can work vice versa as well. So any strain on this thing can actually generate a magnetic field, so they can use it as a sensor in that respect. So you don't want any of those type of effects in a magnetic recording head. So these materials will be chosen to have near zero magnetostriction effect. Now these heads actually have to perform three functions on these hard drives because they've only got the one head. So they have to do both read, write, and also erase as well. And a very crude inductive ferrite head like this will have a ferrite material with the gap in there. The gap is the part that sits over the track and does the recording, and we've got a couple of turns of coil in there, and that generates a three-dimensional, that's important, a three-dimensional magnetic field in here with primarily as much coming out the Y direction onto the platter, because if the platter's, if this thing's flat against your platter like that, then you want it to go out there, and you don't want much in the X direction here, because that's their fringing effects, which then can, if your track width is in there like that, you don't want any fringing effects to affect other tracks. They're not physical bumps like that. I'm just drawing the magnetic tracks in the platter like that. You don't want any fringing effects coming out the X direction here and causing problems with adjacent tracks that you've just written. If you're writing data to here, you don't want to accidentally write another bit into a track that an adjacent track you've just written data to. So these are very complex, and solving the three-dimensional magnetic field equations, they're integrals over space, and there's all sorts of complex stuff that basically, you can't solve them because they're finite distance. They're not like an infinite space and stuff like that. Very difficult, very complex mathematical and three-dimensional field magnetic field solving stuff, and you could do an entire PhD thesis on just magnetic heads. I'm sure many people have. And the same thing goes with the Z direction here. I mean, this platter might be, spinning around in that direction. So, you've got your track on your hard drive there. So your stepper motors come in here for your head, and it's writing to this track here, and this disk is spinning in this direction. You need to write each bit, and you don't want fringing effects in the Z direction either, because that can interfere with the last bit you just wrote on that rotating magnetic disk. And there's lots of complex interactions with the the width of the gap and the distance between the gap and the platter, and the type of material on the platter, and the magnetic fields, and all sorts of stuff, whether or not the cores are laminated, and man, you could analyze these until the cows come home. Now, one of the issues with these heads, especially across these sort of distances, is what's called thermal track shift, and that basically means, well, as it implies, there's a thermal shift. When these things heat up, these heads can physically expand just minute amounts, and then it changes, it affects the position of the head relative to where it's supposed to be on the track. So, as these things warm up, you get expansion of these arms, and that can cause issues with track alignment or track misalignment. So you can also get changes in ambient temperature causing the same thing, and that can be a big deal even at these sort of densities. And we'll take a quick peek inside the actuator motor here, and let's have a look. There's the model number for those playing along at home, and let's pop this away. We've got a bit of spring movement there we go. Check that out, isn't that beautiful? And there's our motor down there. We've got another couple of cogs in there, and looks like we've got a device acting as a heatsink in there. I'm not sure what that sucker's doing at all. So it looks like we've got some sort of spring return gear reduction mechanism here. The motor drives this reduction gear system, which then winds up that spring, and there's a lot of, I can't manually move that. There's a huge amount of torque required to move that sucker. It's a traditional linear actuator motor controlled by these two strips over here. There you go. And what this is a lock mechanism to lock the heads. It actually goes in here like this. So it comes in here, and I can turn that, and boom, I can pull and lock those heads back into position like that. So that locks both sets of heads, and once it's released, it's only like a half turn, like a quarter turn or something like that. So it's, so that's why this thing has that spring return mechanism. It just, I guess if there's, power fails or something, then it automatically, bang, locks the heads back into position like that. Really obvious. So what we've got is we've got like a voice coil in here. It's very much like a speaker, exactly how a speaker works, but instead of moving a cone, we're moving 4 actuator arms, and they're separate banks like that of 4 arms, so they can move independently with these 2 voice coils. Let's check out the voice coil resistance here. If we can get in there, ta-da! Your traditional 8 ohms. Are you thinking what I'm thinking? Absolutely. But of course, this sort of linear actuator is not going to have the same sort of bandwidth as a traditional loudspeaker, purely because we've got a lot more mass in this actuator arm mechanism here than you do in like a paper cone on your traditional loudspeaker. So this thing's probably only going to have a bandwidth of, maybe a kilohertz or 2 at most, just enough to get the access time required for the head. So we can just easily drive our linear actuator with our function generator here. Now put in a sine wave at 10 hertz, and ta-da! There it goes. Works just like a loudspeaker. If I take it right down to 1 volt, for example, we're getting tiny little bit of movement there, if you can see that. And if I up that, 5 volts, 10 volts, maximum of 20 volts on this function gen, there we go. And of course we can adjust the frequency. That's 10 hertz at the moment. So let me adjust that down. 1 hertz. Boom, 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 boom. Fantastic. And if we do a 1 hertz triangle wave there, you can see the more linear motion of it because of the ramp instead of the sine wave. That's a 1 hertz sine wave, and you can see the difference in the ramp. And if we do a 1 hertz square wave, it's going to go bang, 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 bang. And although we're not going to be able to see higher frequencies, we'll certainly be able to hear them. Here we go. I'll put the mic up to it, and you'll be able to hear. That's 1 kilohertz, and then 2, hey, 3, 4, 5, 6, 7, 8, 9, 10 kilohertz. Woohoo! And you probably can't hear that now. That's 15 kilohertz. So there you go. Beauty. I think I'm finally able to get this bastard out of here. Ah, there we go. Oh man, I've been struggling with that locking bar for ages. Mongrel. Precision engineering my ass. Anyway, check it out. We can now, should be able to lift out the entire module. Beauty. So each one of these linear actuators weighs almost 3.4 kilos on its own. That's for 4 actuator arms and 16 heads. Unbelievable, man. But these are all solid, machined linear guides on these things. Absolutely incredible. Now I've taken the screws on this thing off, but I can't seem to get the 2 halves open. I think they've been pressed in there. You can see the those press fit studs in there. It looks like they've been actually, you know, hammered together and fitted in there. So I might have to try and pry it open. It's because you can kind of just see the where you can kind of see the coil in here somewhere. There it is, down in there. You can see that. And we can actually see that coil inside there going over that central bar. Take a look at that. Nice. So I don't think we're actually going to be able to see anything else by taking this thing apart. And I can't, I've got the hammer out and used a bit of percussive maintenance, but I cannot force this thing open. So I might leave it as is, but there's nothing more interesting in there than just that coil going over the central magnet in there. That'd be basically it. And we've got those linear bearings. Look at those. They're just pornographic, really. Oh, ever seen a speaker that good? I've taken off one of the heads here. It's still connected via the flat flex here. There's no way to avoid that. You can see a custom IBM can under there that no doubt contains the head preamp and is soldered directly onto the flat flex there, which of course goes over to the main connector that we've seen before. So I might see if I can pop that can open and see what we can find. I mean, we've got 4 pairs going into this thing from the 4 heads, and then we've got the pairs going out, and that just carries the raw head data back to the main header connector into, as we saw right at the start of the video, into the big rack connector system. So geez, you know, it's basically just a raw data output hard drive. Now please excuse these heads. I've got them falling off all over the place and missing. They're very delicate, but look at this. Here's this interlock bar in here. Here it is right here, and if I pull that back, you can see the heads pinched together like that. So that's part of that lock-in protection bar that was the pain in the ass to get out. It's just a motor to pull the heads back, lock them in place and shut them down. These spring head mechanisms, they're really very delicate little beasts. They would have been carefully designed to apply just the right amount of pressure, you know, and they would have thoroughly tested them. Really tweaked and highly engineered part of hard drive design is just getting the correct pressure there on the heads. I was able to pull the head module out of the flat flex there, and look at that. Looks like it is fully potted. Bummer. But of course that could just be the bottom of it. So we should be able to get in there and maybe, hey, before I open this, I sense a ceramic hybrid coming on. Well, there you go. That was hardly worth popping off at all. Just a bare die mounted on a ceramic substrate there with a couple of like 0603 caps. Anyway, that would no doubt be a custom IBM ASIC. Does all the head drive functionality. Record, read, erase, the whole works. Now, as for these platters, these are very carefully machined aluminium discs, and the material on there is like a cobalt based alloy usually, and that will be sputtered on there in a vacuum deposition process, and you can see that some of it's all just spilled on the edges of the disc there, which doesn't matter a rat's ass really. It's all about the conformity and the thickness of the coating. Now, of course, I was going to try and get these platters out, but I just cannot get my shifter on the top of that, my shifting spanner on there to open it up. I'm going to need some more heavy-duty tools I don't have here in the lab. That one's done up good and tight, unfortunately, but there you have it. That's pretty much all there is to this classic IBM hard drive. And as I said before, if you do have more details on this particular model, we would love to hear about it. So please leave it in the comments or go to the EEV blog forum, which is where all the action's going to happen on the talk of this sucker. So the technology in this thing is pretty basic as far as modern hard drives go, but it is incredibly machined. These linear actuators, fantastic. Just love it. Brilliant stuff. And the magnetic density on these platters, the 11-inch platters in this thing, is absolutely nothing compared to modern hard drives. And as you saw, there's no controller in this thing at all. The controller would be in the rack hard drive system, because all we've got are these little head preamps in there, which we saw, and that's basically it. It's just amplifying the signal and then driving it along right into the backplane bus. And well, that's going to be one hell of a controller when it's got to control all these hard drives with all that raw data coming in. But this thing's only 10 megabytes, not huge data rate. But anyway, I hope you enjoyed it. That is the most expensive teardown to date. It's worth $250,000. Do you believe it? But hey, we're talking about banks here. Catch you next time. And of course, no teardown's complete without sacrificing some blood to the teardown gods.